Good morning, ladies and gentlemen. Thank you for giving us the opportunity to present our project entitled T-EVA, Wearable Mechatronic Embedded System for Upper Limbs Temperature Monitoring during Extravehicular Activities on Mars. My name is José Cornejo. The teams of authors are Paul Palacios, Walter Castillo, Milton, Rivera, Jinmi, Lezama, and Juan, Chavez. This project is developed under the supervision and management of Bioastronautics and Space Mechatronics Research Group, which was founded in 2015 and established in January 2019 as the first professional research group of its kind in Latin America as part of the Mars Society. Currently, it is an autonomous international group. We have members from Ibero-American countries working together to develop innovative technologies to support space human medicine, space veterinary medicine, and space physics and engineering divisions to improve the quality of life and explorations on Earth and space. The main topics that we are going to develop are introduction, materials and methods, and conclusion and further work. When astronauts explore the surface of Mars and performing extravehicular activities, they will be exposed to extreme environmental conditions that may cause thermal homeostasis imbalance, loss of sensitivity, peripheral cyanosis, and heat exhaustion. For this reason, it is necessary to integrate biomechatronic systems into the spacesuit with the objective to monitor of vital signs such as the body temperature. Therefore, a research study has been conducted from 2019, resulting in the proposed project named T-EVA, which is classified as a wearable medical device. It consists of 6 sensors anatomically distributed in the upper plane of the human body, where 4 of them are placed in the upper limbs because of the temperature in these areas is variable due to the constant peripheral vascular regulation, and also 1 sensor in the thoracic region, and last, 1 on the forehead. This work process starts sending data to a microcontroller in order to convert, also process and transmit information to the bracelet and also to the remote monitoring center that will allow visualizing the temperature in real time. Furthermore, T-EVA has been chosen in 2020 by the Mars Society Peru to be used and tested at the Mars Desert Research Station in US in order to be part of the Team Peru 6. The first step of the project about the conceptual design was presented at 2020 IEEE Engineering International Research Conference, and also the integration of T-EVA with smart globe to control a rover was presented at 2021 IEEE International IoT Electronics and Mechatronics Conference, both published at IEEE Explore and Scopus. Currently, T-EVA is under development and deep engineering analysis about the strength of materials, the telecommunication technologies and protocols, and also improvements of the electrical and electronic design. It is expected to perform the mission on 2022. So the main purpose of this work is to obtain real-time values of body temperature during the exposure in extreme environments in order to prevent hypothermia or hyperthermia symptoms that may affect the performance and health of the astronauts. A Mars cold environment can be attributed to a low surface conductivity, a thin atmosphere, and a considerable distance from the sun. This exposure has been proven to affect physical and cognitive performance. Both findings have a considerable impact. The human body can be conceptualized as a thermal machine that exchanges energy with its environment through humidity and heat. Exposure to extreme temperatures may cause hypothermia or hyperthermia, ending in multiple clinical manifestations, heat and cold stress respectively. Thermal comfort implies a balance between the heat produced and the heat transfer mechanisms through the effector system, vasoconstriction or vasodilatation. depending on the conditioning factors. The need for optimization of monitoring processes of physiological parameters under harsh environment conditions required the design of new sensors. This analysis allows the creation of wearable device T-EVA capable of constant estimation of body thermoregulation. This device tends to be a bailiff, non-invasive alternative, small, compact, adaptable to other multiparametric devices, facilitating telemetry monitoring and timely medical management. As you can see here in the figure, first there is one sensor in the forehead, two in the upper arm, and also two in the forearms. And then the last is here in the chest. And now another co-author, Paul Palacios, is going to present this part of the project.
Good afternoon, everyone. Can you hear me?
Yes.
I'm Paul Palacios. It's a pleasure to be able to participate in this symposium. Materials and methods, electronics and embedded system, peripheral sensor, left and right sides. The sensor is joined to the case with screws. The box top is put together with a case using bolts. It has the lips on its base, while the grooves will be on the switch. When pressing one against each other, they will fit. Next slide. Okay, we can see the table. The table 3 is the components and the autonomy in hours of the T-EVA system, including the consumption for each module, use microcontroller, sensor BMP module, NRF, multiplexer, and module 40x6. And the autonomy of the bracelet, it's more than 5 hours. And when that it's over, the body core continue work for 5 hours, sending information to the base station to keep them informed to the astronaut status. Next slide. Okay, the electronics and embedded system body core board. For the requirements of the T-EVA system, the STM32F103 was chosen as the microcontroller of the body core board. The module multiplexer is a TC8 that will provide us with 8 channel with the I2C protocol, 6 channel for the temperature sensor, and 2 channel for reserve. The sensor temperature BMP2H0 complying with the range from -40 degrees to 85 degrees. The circuit TP4056 is used to charge the LiPo battery, the 3.7 volts and 2000 milliampere hours. The module NRF as an emitter for radio frequency communication to the bracelet and base station. And the bracelet for the requirements and STM 32F103 was used as a microcontroller, and the circuit TP4056 load through a micro type C connection that give us the functionality of being able to supply power while the battery is connected. LCD touch screen, 2.4 inches, and the model NRF as a receiver. The next slide, please. Okay. Peripheral sensor left and right. The temperature and pressure measurement in this module is optimized in terms of power consumption and is used to collect data from the environment. We can see the table 4 represent of parameters for further estimation of reliability for each components, solder joints, vibration, moisture failure rates. There was a not failure rate, so it can be assumed that the resulting value of the duration is 9,814 hours. In the table 5, pi THC y minus CS and pi THC y underscore S minus J represent the impact of thermal cycling stress of the reliability of the case and the solder joints of semiconductor components. The next is okay. The sensor BMP and the microcontroller STM and NRF module to design the scheme of temperature system can relies on real-time temperature acquisition, has some advantage compared with the wire system, such as a low complexity, low cost, and low power consumption. The module NRF topology was chosen as the wireless communication, satisfied all the specific requirements to establish a stable connection between the astronaut and the base station. It allowed to the link of up to 6 unique nodes in the network, which give advantage for scaling up the network and implementing robust communication. Confirm the benefits of the NRF topology over ZigBee and Bluetooth solutions. We can see the parameters, the range, baud rate, no, the NRF module, Wi-Fi, and ZigBee. The next slide. In the figure 5, we can see the braille screen interface view. The slide shows the behavior of the body's temperature in extreme environment located in the brace. In the figure 6, according to the simulation, T-EVA will show in real time the temperature value that be seen, values that will be seen in LCD graphic screen. which is located on the bracelet.
Excellent. This is it sounds really interesting. We're just about out of time. Victor, if you could wrap it up next minute or two. If you want to wrap it up the next minute or two, or speak more for one more minute, you're welcome.
Okay. Listo. Yeah, continue. Once the Marshall exploration started, we can see the figure workflow diagram. Start, switch on off, main, if yes, mainboard turn on, sensor reading, data conversion, data save on microcontroller, and send data to the bracelet, and show the parameters, and send to the remote monitoring center. The next slide, please.
Perfect. To finish this project, the explanation of the project, well, this is a conceptual design of a bracelet. These measurements has the measurements of each author in the wrist. So also we proposed the materials, as you can see there, the titanium, the grade 2 or maybe grade 5. And now this conceptual design is under development. So we will prototype of this project maybe in January 2022, and in order to have this prototype ready to send to the MDRS on May 2022. We think that this project will be very useful, not only for maybe astronauts, and also be useful for maybe here on Earth, in order to obtain physical values that allow us to understand how the human body behaves, not only in space, also on Earth. So, well, thank you very much for your invitation. This is a pleasure to be here today.
Thanks so much, Jose. And
just a comment. That's a very good design, very impressive design. Good work. One of the things that takes the astronauts one of the tasks that takes the astronauts so long is to put on their biopack, which has all of these sensors in it. So anything that can expedite that process of getting in and out of the EVA mode would be most helpful. So this is an excellent design. Good job.
Thank you very much. We appreciate that. Thank you.
Thank you so much.